Good morning, honors chemistry students. Today's video lesson is going to be over titration calculations and neutralization reactions. Titration calculations is a unique concept to honors chemistry. It's one of those things that we do with honors that we do not typically do with our normal general students. So we are just continuing our discussions on acid-base chemistry. Starting with a little bit of a review of neutralization reactions. So if we remember back to Unit 3A, when we learned about chemical reactions, we learned that a neutralization reaction occurs when you mix an acid and a base. Now for us, we are going to specifically focus on a strong acid with a strong base. The reason? The calculations are much simpler when we're looking at strong acids, strong bases. So, a neutralization reaction is simply when you mix an acid and a base and they come together to form salt and water. Now, because we are looking at strong acids and strong bases, we can actually use their concentrations to predict how much of the other we would need to neutralize a certain amount. Or we could determine the concentration, the molarity of an unknown acid or base if I know the concentration of one and I know the volume of both of them used. So this is the nice thing, is if we can actually do calculations to predict how much stuff we're going to need to do an experiment or how much product we're going to make from an experiment. So titration is the process of adding a known amount of a known concentration. So I've got something that I know its volume and its concentration, and we use that to determine the concentration of another solution. That process is called titration. Your known solution is sometimes called the standard solution. It also might be called the stock solution, but it's the thing that I actually know its concentration of. Either A, I've gotten it off the shelf in the laboratory and I'm taking it at face value that, the person that made that solution knows what they're talking about. Or B, I've used the masses of my strong acid or my strong bases to determine the concentration of the substance in the container. Now, when we are doing titrations in a laboratory setting, which we won't have the opportunity to do this semester, but when we do them, we use what's called a burette. And it's a really long, skinny, singular glass tube. Really expensive piece of glassware. But what it does is it allows us to add very precise volumes and see exact measurements of the volumes of liquid added. Now, most of the examples that we're going to look at, our acids and our bases do mix to a 1-to-1 ratio, but not all of them are 1-to-1. You will see some that are 2-to-1 or 1-to-2. So it is important that you pay attention to that balanced chemical reactions. Just like with stoichiometry, that mole ratio was important in doing conversions. Same thing with titrations. If they're not a 1-to-1 ratio, you're going to need to look at your stoichiometric conversions to look at the mole ratio and get rid or use the right coefficients. So this illustration is kind of showing a burette. The thing about a burette is that they are numbered a little bit funky. They have, I went blank for a second. 0 at the top and like 50 at the bottom if it's a 50 milliliters. So usually with titration, we will use some type of an indicator. The one that's shown in this illustration is phenolphthalein. Phenolphthalein goes from clear to blue, but we also have a universal indicator that turns like 3 or 4 different colors. So either way, that color change would let us know that we have a change in pH. You can also use a pH meter that tracks the change in pH over time. We just don't have that equipment here at the high school. So what we do is we start adding. We know how much acid is in this container. So let's say I know that there is 25 milliliters of acid in this container, but I don't know its concentration. I do not know its molarity. I know the molarity of my base. So the molarity of the base is, 0.5 molar. Well, we measure and we add base to the reaction until we get to a point where that color change occurs. That color change is called the end point. The end point of the titration is what we are looking for. Most of the time you select your indicator so that the end point is when the number of moles of your acid equals the number of moles of your base, when they have completely and totally canceled and balanced each other out. The equivalence point and the end point tend to be the same. So my equivalence point is when the number of moles of hydrogen ions and the number of moles of hydroxide ions are equal. That's hence equivalence. Well, when they are equal, that tends to be where my indicator changes the color. So the end point and the equivalence point tends to be at a set space. So let's say we had, I don't know, we're just going to make that one a 0. We had 0, and we went from 0 down to 30 milliliters. So we went from 0 to 30. We know that we put 30 milliliters of that 0.5 molar base solution. Well, if we know how much base we added, we can determine the concentration of the acid. We are using knowns to figure out an unknown. When you're looking at titration problems, there are generally 2 major types of problems. And I'm going to do examples of both. Your first type of problem is where you are trying to determine the number of milliliters needed to complete our neutralization reaction. So it's asking you for a final volume or a volume needed. With any type of a conversion or calculation, you've of course got to have that balanced equation. This has not changed from Stoic. So that is still the same as what we saw in Unit 3B. If I don't give you that balanced equation, make certain you get the balanced equation. So you're going to use the molarity and the volume to determine the number of moles of your known substance. Remember, molarity equals moles over liters. So in order to get the moles of my known substance, I have to take my molarity times my liters. Once you know your number of moles, you use your mole ratio to convert from one substance to the other. Once you have your other substance, you're going to use the molarity and the moles to determine the volume. So remember that liters equals moles divided by molarity. So in order to determine the volume, liters equals moles divided by molarity. I'm going to tell you this now, 9 times out of 10, we don't want liters. We want milliliters. So you're going to have to do an additional conversion to get to milliliters. So let's look at an example. We've got 2.1 molar sodium hydroxide reacting with 450 milliliters of sulfuric acid. So first thing we need is that balanced equation. Sodium hydroxide and sulfuric acid react as a 2-to-1 ratio. It takes 2 sodium hydroxides to balance out 1 sulfuric acid. So we've got our we've got our equation. Now we can find the moles of our known amount. Well, I only have one thing in which I know the volume and the molarity. So whether it tells me or not, this thing that I have the volume and the moles of is my known solution, or my stock solution, whether it tells you that or not. So in order to get molarity, badness reigns, in order to get moles, I need molarity times liters. Well, 435 milliliters is the equivalent to 0.435 liters. I would hope by now, my honors babies, you could do that conversion in your head, but if not, you of course are highly encouraged to show that conversion. I was going to say I don't think I did, and I did not. So to get moles, I'm going to take 0.435 times 1.75. Notice I switched my units here. I switched out that big M for moles over liters. That way I can visually see that liters cancels and we are left with mole. No, you don't need to do that. I just did that so that you can actually see how our units are canceling out. Handy dandy calculator. 0.435 times 1.75 gives me 0.76. So this is the moles of acid. Well, my acid reacts to a 2-to-1 ratio. So I'm going to have to use my mole ratio to get rid of moles of acid and go to the moles of the base. So notice I have 2 moles on top because I'm trying to get to the base, and I've got 1 on bottom because I'm trying to get rid of the acid. Now that we know our moles of base, we can determine the volume. We can calculate our volume. It did not specify whether it was liters or milliliters. So for this particular problem, I would have to accept both. So my volume, liters equals moles over molarity. So my volume equals my moles over my molarity. I'm not really sure why I showed it that way. So we're going to put it back the way I would normally do it. 2.1 mole per liters. So that big M I just replaced with its other unit. I've got liters at the bottom of a fraction. We can see that the moles cancel. We are left with liters, since liters is at the bottom of a fraction. So 2 bottoms there. It ends up coming to the top. So handy dandy calculator gives me 0.75 liters. It did not specify to convert to milliliters, so I would have accepted either or. So 0.725 liters is 725 milliliters. Right. So pause the video, give this one a try. Actually, I'll give you the balanced equation. Now give it a try. So same type of problem. We've got to find our moles, use our mole ratio, and then determine the volume. So to find my moles, I'm going to go ahead and turn my milliliters to liters. I'm going to take my moles equals molarity times liters. So I'm going to take my 0.355 liters times 2.50 molar. Remember, that big M is the same thing as saying little moles over liters. So we can see that the liters cancels. Handy dandy calculator, 0.355 times 2.5 gives me 0.8875. Keep all of your numbers, don't round to significant figures until the end. And this is my moles of magnesium hydroxide.
Incoming email.
Now we've got to use my mole ratio.
Incoming email.
And yes, technically you don't have to rewrite that moles. You could just continue your calculation, but I don't have enough space, so I'm going to rewrite it. So we're getting rid of magnesium hydroxide, which means 1 mole goes on bottom and 2 moles goes on top because we're trying to get to the hydrochloric acid. Times 2 gives me 1.775 moles of acid. So I know my moles of acid. Now I need to find my volume. So liters equals moles over molarity. So my liters is going to equal my 1.7, crap sauce, 1.775 moles divided by the molarity of the acid in the problem, 3.3 molar. Again, remember, big M is the same thing as mole over liter. So moles cancels. We are left with liters. And we've got 0.5378, so 2 sig figs. 2 sig figs. So 0.54 liters or 540 milliliters. And I apparently can't number. So that's 2 examples of our first type of problem. You are trying to find volume. The second type of problem is one in which you are trying to find molarity. You will notice the first 3 steps are the same. Whether I'm trying to find volume or I'm trying to find molarity, the first part's going to be the same. So the only thing that changes is at the end, we're going to use the moles and the volume to find molarity. So steps 1, 2, and 3 are exactly the same. We got to have the equation. We got to use molarity and moles to find, use molarity and volume to find moles, find my mole ratio, and then use the volume in the problem to determine the molarity of your unknown. So let's look at this example. Titration reveals that 22.5 milliliters of 0.2 molar, 2.0 molar nitric acid are required to neutralize 20 milliliters of calcium hydroxide. There should be a dot behind that milliliters. What's the molarity of the hydrogen calcium hydroxide? So we have our balanced equation. I can't play with milliliters, so I'm going to turn this into liters. So that 22.5, I've got to divide by 1,000. In fact, I'm going to go ahead and do that to both and just turn them into liters so I have them on the page. I did that with all of them. Yep, I did. So molarity times volume will give me moles. 2.0 molar times 0.0225 liters will give me my moles. I have 0.045 moles of nitric acid, HNO3. Now that I know my moles of nitric acid, I can find the moles of my base. That means I'm going to use my mole ratio. Oops, HNO3. So the acid has to go on bottom, which means 2 moles goes with it. The base has to go on top, so 1 mole on top. And handy dandy calculator tells me that I've got 0.0225 moles of my base. All right. Now that I got my moles of my base, I can determine the molarity of my unknown. So it tells me that we used 20 milliliters in our solution. So 0.0225, my moles times my liters will give me my molarity. So this base is 1.125 molar. Oops, and I forgot my calcium hydroxide here. Okay. So you guys and gals try second example for the second type of problem. Hi, kitty. Okay. And just like before, I'm going to give you the balanced equation. So use your molarity and your moles. Bad mysteries. Use your molarity and your volume to find moles. Then mole ratio to get to the other substance. And then use your moles and your other volume to find the molarity of the other thing. So this one we are starting with the base. I'm going to go ahead and convert my milliliters to liters. 0.112 liters, and there needs to be a dot behind that 5. 0.050 liters. So we're going to use our 0.0112 liters and our 3.5 molar to find the molarity. Molarity times liters gives me moles. Molarities times liters gives me moles. Remember that big M is saying the same thing as mole over liter. So the liters cancel. Now that we have moles of barium hydroxide, we use our mole ratio. This time it needs to be a 1 on bottom because my barium hydroxide has a 1. It's a 2 on top because the acid has a 2. Now that we know the moles of acid, we can use the moles of acid and the volume of acid to determine the molarity. So 0.0784 divided by my volume of 0.050. So handy dandy calculator, if I did that correctly, crap sauce, 0.784 divided by 0.050 gives me, ooh, I may have rounded something funky, but that's fine. 1.56 molar perchloric acid solution. That is it for titration calculations. That's all for my honor students. Make certain if you've got questions about the practice that you're coming to my open office hours either today or tomorrow to get some help with the practice. I shall see y'all next time we meet.